Hi everybody and welcome. Today we're going to be talking about systems of equations that use word problems. So combining two of our favorite things in the world, the solving systems with nice long word problem sentences here. I think honestly though today is one of the more useful days that we're going to see for solving systems because it really does take this and apply it directly to the real world. So everything that we're going to see with these questions are things that you might actually find yourself looking at in real life. So the first thing that we want to talk about from a more general perspective though, and this will come up a few times throughout this unit, is are we even able to solve the system that we're looking at? And there is a way, before you even start doing any math at all, just by looking at something to know, are you able to solve it? So we're going to start off by defining this as something called multiple unknowns. And another word for unknown we could just use would be something like variable, for example. So like if you have x and y, those are two variables. You have two things that are unknown that you don't know. And there's actually a rule for this. And you need one equation per one unknown variable in order to solve. So if you have x and y that you're trying to solve for, if you don't have two equations, well, you just can't do it. There's no way to do it. So we're going to see a few examples as we go through. So things that you've seen in years past. 2x plus 3 equals 5. In this, you have one variable, one unknown, and there is one equation. So yes, you should be able to get an answer for x. Things that we were doing last week. X plus y equals 12, and 3x minus y equals 50. If you look at this, we have x and we have y. So those are two variables, two unknowns, and we have two equations. So because of that, yes, you are able to solve. But if we had something like x plus y plus z equals 5, and y minus z equals 12, if we look at this, we have 1, 2, 3 variables, but we only have 1, 2 equations. So there is no way that you're able to solve for all three of these. So if you ever saw something like that before even starting, you know, okay, I can't do this one. So just something to keep in mind if you ever find yourself stuck on maybe a trick question that comes up here or there. Just always double check if you have multiple variables that the number of equations that you're given matches. So a couple of quick things. First, we want to make sure when we're solving these, specifically with word problems, we do want to fully annotate the question. Second, you're going to want to set up an equation with your x and y variables. So if there are two unknowns, we'll set those up using x and y. It doesn't have to be x and y, but basically you just have your two variables you set up. If you prefer using, a and b, that's totally fine. Often, you will have one equation that involves just the quantity, and this will just be the total number of items purchased, or basically just the number of things that we're looking at. And then often one equation will involve each term that deals with money. So usually when these split up, you'll have one that has dollar amounts, and then you'll have one that is just counting. So just a good rule of thumb there. And then lastly, you can solve your system of equations. So let's take a look at what we have here. So first, let's annotate. So a store sells two types of flowers, daisies and tulips. And let's start color coding. We purchased 13 flowers, so that's a quantity. That's a number. We can count out 13 of them for $98. We'll put it in green because $98 deals with money. So daisies cost $8, more money. Tulips cost $7, more money. How much of each did you purchase? Okay, So first, quantity equation. We have daisies and tulips. So maybe I'll put X for daisies and Y for tulips. So I know if I add daisies and tulips together, our quantity, our total in blue, is 13. So basically that's just saying if we add everything together and count it up, it equals 13. Second, daisies, our X value, cost $8. So for each each daisy that we buy, it's $8. And tulips are $7. So for each tulip we buy, that costs us $7. And we know that if we multiply all of that money together, it should get us $98. So that is basically what we're looking at for our system. We have our quantity equation first, just counting the number of things we have. And second, we have our money equation, saying how much do each of these things that we have, how much do they cost? So you have a bunch of different options to solve this one. As you can see, x's are on top of x's, y's are on top of y's, equal signs on top of equal signs. This does line up nicely for for elimination, but you also could substitute if you choose, but again, totally up to you. So two different ways to do it. I'll just choose, because everything's lined up nicely, I'm gonna do some elimination here. So we have 8x and 7y. But nothing cancels out, so we're going to have to make it so that it does. And the only thing that we could get to cancel out 7y, for example, would be minus 7y. So we have to do for our first equation is see, okay, what would we multiply this equation by that would give us minus 7 for y? Well, the answer is minus 7. So if we multiply all three of these terms by minus 7, so minus 7 times x, minus 7 times y, and then finally minus 7 times 13, that should give us what we're looking for here. So lining these things up, straight up and straight down, we end up with 1x. 8 minus 7 is just x, equals, and then 98 minus 91 gets us 7, and then 7y minus 7y cancels out, leaves us with nothing. So what we see is we buy 7 x's. Well, what is 7 x's? Well, that is daisies. So x equals 7 daisies. So we can take our x value and now plug it back into that original equation. So I'll actually have you do that now. So if we buy 7 daisies, how many tulips? All right, so if we plug this back in, what we're gonna see is we can use the first equation. I think it'd probably be the easiest one. X plus y is 13. We know that x is 7. So now what we can do is just subtract 7 from both sides. And we'll be left with y equals 6 tulips. So checking our work here, 7 daisies and 6 tulips, that is 13 total flowers. And then if we were to multiply our 7 daisies times $8, and then our 6 tulips times $7, that actually should add up to 98 as well. So it fits. So both of those things work. So that's an example of basically what we're looking for here with a nice word problem that uses money and counting, basically a quantity and a dollar amount equation. All right, our second equation here, two numbers add up to 12 and have a difference of 5. So a lot of us are going to be tempted right now to be like, oh, I'm just going to start punching stuff into my calculator and do this in my head. Well, that's great if you can do that, but when the numbers get really big, you just won't be able to. So we are practicing intentionally on a question that you might be able to solve in your head, because we want to get the steps down on numbers that are smaller before we jump into, the whole big ones. So what I would say is, if you are someone right now that's really tempted to just solve this, don't. Practice doing it the way where we set it up using a system, because that's going to be basically setting you up to be successful in the future when you're not able to plug these basically into your calculator and just see what works out. So again, try to stay with us and try to take these good notes here, because it's going to pay off big time when the numbers are too much to just brute force in your head. So two numbers add up to 12. So there's an operation adding up to 12, but have a difference, another operation of 5. So addition gets us 12, so something plus something, so we'll say x plus y gets us 12. But subtraction, so if we subtract these, x minus y gets us 5. What are they? Okay, so there's your system. So I'm going to pause the video here and actually have you punch in what is x and what is y in our system. All right, so from here, actually another nice one. We can line these up straight up and straight down. And what we'll see is, make my lines wrong. Positive x and positive x, that's 2 x's. Positive y minus y, those cancel to 0. And we have equals. and 12 and 5 add together to get us 17. So we have 2x equals 17. We can divide both sides by 2, and we'll get an answer of x equals 8.5. So now that we've done that, we get to choose our favorite equation and plug it back into. So it shouldn't make a difference here, but I'll just do the first one. No negative sign, so I like that. Makes it a little bit easier. So subtract 8.5 from both sides, and y should give us 3.5. So double check this real quick. 8.5 and 3.5 do add up to 12. 8.5 minus 3.5 is 5. So our two answers here are 8.5 and 3.5. And this might have been a harder one because we do see decimals come up. So the nice thing about systems is it doesn't matter, decimals, any of those types of numbers, big, small, anything in between, it'll always work. You'll always be able to solve. All right, so some practice questions coming up. Good luck. If you need any help, as always, check in with us, but you are ready to get started. Thanks for watching.